Hello everyone. Today, we'll organize the ideas from quantum theory to the structure of the universe as clearly and accurately as possible.
It sounds difficult, but I'll do my best to follow.
First, the most important point in quantum mechanics is not the question are electrons or light waves or particles.
What? But that's the famous part.
The essence is the concept of the state vector. What physically exists is neither electrons nor waves, but an abstract state.
And that's the state vector?
Exactly. The one written as psi. The physical quantities we observe, wave or particle behavior, position, momentum, wave number, frequency, are just slices of the state vector taken in the basis of the observing system.
So we're just peeking at the part we want to see.
In quantum mechanics, a state evolves in time according to the Hamiltonian H.
That's the Schrödinger equation.
Yes, IH bar d psi dt equals H psi. If you knew all information about the entire universe, the whole universe would evolve unitarily in the same way. Both the future state and the past state are determined.
So the universe is deterministic?
The laws governing the whole universe are deterministic, but measurement outcomes are probabilistic. Observation is the operation of projecting the state vector onto the basis of the measuring system.
A projection, right.
Even the projected state still contains many possible measurement outcomes.
And from those, we obtain one actual result. You can't escape the probabilistic interpretation.
Up to here was quantum theory. Next is general relativity.
The one where space-time curves.
General relativity imposes the condition that physical laws must look the same in any coordinate system.
General coordinate invariance.
As a result, the Hamiltonian of spacetime becomes zero as a constraint.
Zero energy?
No. It means the generator of time evolution becomes a gauge. That's why the four-dimensional spacetime structure itself does not undergo time evolution.
Then is the universe frozen?
The structure of four-dimensional spacetime is static. But local coordinates move. When local coordinates, meaning the local metric g mu nu, xt, change, we feel motion.
So only the appearance is changing.
Then naturally the question arises, how is the time evolution of the local metric determined? In holographic theory, the boundary quantum system generates the motion of spacetime.
What is the boundary?
It's a special surface within the four-dimensional spacetime structure where physical information is defined and where a generator of time evolution can exist. That's what we call the boundary.
So the boundary is the engine?
Exactly. The Hamiltonian on the boundary produces the apparent time evolution of spacetime. Now let's talk about the many worlds interpretation.
The one where the world splits, or where many bubble universes exist.
That's a misunderstanding. Popular books oversimplified it.
If the world splits, it sounds like parallel worlds keep multiplying over time.
And if you imagine many bubble universes, you end up needing a higher level spacetime to place those bubbles in.
But in the Big Bang model, they just say the universe emerged from a vacuum state. Before that, even space and time didn't exist. That's contradictory.
The correct picture is that the state vector of the entire universe, psi, simply has the structure of a superposition of different four-dimensional spacetimes world_I with different physical structures. These different four-dimensional spacetimes world_I are what we call different worlds. In the other video, the measurement problem and information loss, we learned about decoherence. The global state of the universe evolves deterministically, but the information accessible to us leaks irreversibly into the environment. As a result, the sub-universe we can observe appears classical. Everett called the collection of these sub-universes branching worlds. They become almost orthogonal and can no longer interfere.
That's why we can't observe the other worlds. But the information isn't gone?
Right. It's preserved in the entire universe, but it spreads out in a way we can't recover. That's the true nature of the irreversibility of time. The world doesn't split. And there aren't other bubble universes floating around. The state vector simply has a structure containing many almost orthogonal sub-universes.
If we interpret that as many worlds, there's no contradiction.
Popular books say the world splits or the universe multiplies like bubbles, but physically that's incorrect.
It sounds cool, but it's a misunderstanding.
The correct view is, a single state vector contains mutually orthogonal physical states. So the universe is a single state vector, within which all possible physical states coexist.
It's more mathematical than I expected.
An observation means experiencing one of those histories.
We're walking along one branch of it?
At this point, there's basically one unresolved problem in quantum theory.
What is it?
Why we are experiencing this particular measurement outcome.
No one knows yet?
Not yet. But remember this. Everything we've discussed assumes the validity of holographic theory and the existence of a boundary.
And holographic theory itself still has unresolved issues.
Yes. Why must nature have a holographic structure? Does a boundary corresponding to the entire universe actually exist?
The universe is still full of mysteries.